Okay, so let's make a start for the second speaker of this afternoon session. Our speaker is Bruno Tuffin, who is currently a research director in INRIA and RAN. He did his PhD in the University of RAN 1997, and he has around 150 articles, books, conference proceedings, and reports, etc. He's an expert in Monte Carlo, quasi-Monte Carlo, internet pricing models, and the performance and reliability of communication networks. And he's going to speak on a central limit theorem and confidence interval for randomized quasi-Monte Carlo methods. So please take it away. Thank you.
Thank you, and thank you for the invitation. So what I'm going to present today is not related to relevance. So it's what I presented during a seminar 1 year ago, probably to many people of this audience. So I wanted to do something else. So what I'm going to present is also a joint work with Marvin Nakayama from New Jersey Institute of Technology, but it's more related to randomized Quasi-Monte Carlo methods, which were methods that I was really working on during my PhD, so a long time ago, as you said. Okay, so, and the motivation is, so I will explain briefly Monte Carlo, Quasi-Monte Carlo and randomized Quasi-Monte Carlo methods, but the motivation is that we usually use randomized Quasi-Monte Carlo methods by applying a central limit theorem, but we don't have really theoretical proof that this confidence interval that we are obtaining is valid. So we are here trying to get some sufficient conditions for applying a central limit theorem on randomized Quasi-Monte Carlo methods. Okay. Okay, so again, the motivation. So first, what we want to estimate is the quantity mu, which is the expected value of h of u, where u is a uniform over 0, 1 to the s. That's a typical Quasi-Monte Carlo framework. So you can generalize it, but in simulation, restricting yourself to uniforms like this is not that restrictive. Okay, so if you very briefly, and I will describe it more during next slides. If you use Monte Carlo methods, then you will, if you are on the square, so you will take random points. If you use Quasi-Monte Carlo methods, you use points that are much more uniformly spread, much better spread over the square. And if you use randomized Quasi-Monte Carlo methods, then you just randomize these points of Quasi-Monte Carlo, but without losing their good repartition structure. And you can, the idea is to apply independent randomization like this, and to apply a central limit theorem over independent randomization. But as I said, the central limit theorem that is applied like this by using independent randomization is not proven for many RQMC settings. And our goal here is to find general conditions, sufficient conditions, but at least to give first conditions for RQMC to ensure that you have a central limit theorem and an asymptotically valid confidence interval. So I will review first Monte Carlo, Quasi-Monte Carlo, randomized Quasi-Monte Carlo, and give a very general result on randomized Quasi-Monte Carlo and central limit theorem for that. And I will give some corollaries in some specific context that will describe how sufficient conditions perform and what are the results. So that's a work in progress with Marvin Nakayama. So we still have many things to do on this. So that's also why it's interesting to talk about it to get some feedback. So again, so the same figure here, very briefly, because you all know it. What is Monte Carlo in in the case where we want to estimate the mean mu of h of u, where u is the uniform over 0, 1 to the s. So you take random points and you estimate your the expected value as the average over all your random points. So as you know, you have the central limit theorem, which tells you that the standardized error here converges to a Gaussian distribution. And you can get, thanks to that, a confidence interval by estimating, even by estimating the variance of your estimator. And we all know that you get an asymptotically valid confidence interval that we wrote AVCI, meaning that even by estimating the variance, the probability that mu is in the interval here is converging to the confidence level that you wish. And the important one important measure is the root mean square error, which is basically the half proportional to the half width of your confidence interval. The root mean square error is the standard deviation divided by the square root of n. So many people say that it's quite slow, since you need to multiply by 100 to get 10 times smaller confidence interval, and so on. But you can also argue that this rate of convergence, n to the minus 1/2, is independent of the dimension s of the problem, which is a very strong property. So, based on the idea that this convergence rate is quite slow, and the fact that you select points randomly, so many people were thinking of trying to do something more intelligently somehow, by trying to just choose the points, not randomly, but in a way that they are very well spread over the domain of interest. Here, the square. So instead of using random points, you use deterministic points, and you use a sequence of Xi, and we use what would be called a low discrepancy sequence, Xi, which is deterministic. So, and instead of choosing the points randomly, you try to spread them very well. Here we have an example, which is a lattice. I will describe another example on the next slide, which is less obvious somehow. And using this kind of repartition of points, you can expect the error to be smaller than with Monte Carlo. So here's a lattice. There are many constructions for that. I don't describe the construction of points because it would take some time, but you have many in the literature. I can give you some references if you want. So on the construction of lattices, depending on the size of your sequence and so on. But you can see you have other examples. Here again, I give the example of what is called a digital net. It can be a Sobol sequence, a Four sequence, or a Niederreiter sequence. So here, with 16 points, so they look like they're random, but they have very good properties. So those 16 points are very well distributed in a sense that if I cut the domain in two, I have the right proportion of points on each side. If I cut it in two like this, also the right proportion of points, 8 on each interval. If I cut it in 4, I have 4 points in each square. In rectangles divided in four like this, also the right proportion of points. If I divide it in 8, again, 2 points in each rectangle, 2 points in each rectangle. And even if I divide it in 16 like this, I have the right proportion of points. I can use many constructions like this just to show that this sequence has very good properties that can be used later on to prove good convergence rates. And again, 16 like this, 1 point, and so on. So the advantage of Quasi-Monte Carlo is to have a fast convergence rate when we're able to show it. So again, Quasi-Monte Carlo uses deterministic points. So you have a sequence Ci and you use the average value over all your points of the sequence. And how to determine the error? So there is a bound which is well known in the domain, which is called the Cox-Malauka bound, which tells you that the error that you make with your estimation here, it's upper bounded by a product of two terms which separates the properties of the integrand h and the property of the sequence. So it depends on something that depends only of the integrand and something that depends only of the sequence. VHK is called the variations of RDN curves, which expresses the some kind of roughness of H. I will give more details on the next slide. And the DN star is a star discrepancy, or sometimes I just call it the discrepancy of the sequence. And with the construction of points that I described before, for sequence, Sobol sequence, Niederreiter sequence on lattices, we have a discrepancy that is decreasing in O of n to the minus 1 log of n to the s, which is basically n to the minus 1. Okay, so we go as soon as we have bounded variations in the sense of RDN curves, as soon as this is bounded, then we have a convergence rate which is much faster than Monte Carlo. So in this case, everybody could say, so what's the point of using Monte Carlo if Quasi-Monte Carlo is much faster? So there are, of course, difficulties to apply it. So one that I'm not describing too much here is the fact that when the dimension S is large, it takes quite a long time to get this convergence rate as a better than Monte Carlo, but that's not the only point. And one of the issues that with Quasi-Monte Carlo is that the error estimation is very difficult. So as I said, we have two components, the variations in the sense of RDN curves and discrepancy. And the variations in the sense of RDN curves, it can be, it is decomposed actually in a sum of 2 to the s minus 1 other variations, which are the traditional variations in the sense of Vitali. So it explodes as soon as S increases. So it's really hard to get something that is interesting to use in practice. And even in many cases, this variation in the sense of RDN curves, it is infinite. And I can use a simple example that I get from Nicolas Boulot. I got from Nicolas Boulot in dimension 3, function h, which is the minimum of the sum of the two variables on one. So this simple function has an infinite variation. And Quasi-Monte Carlo is converging very fast on this example, but the bound, Cox-Malauka bound, it cannot be used because we have an infinite variations in the sense of RDN curves. So this component is kind of useless. So it's already enough to say that the bound is useless in practice. But even if you think about the discrepancy, which is the measure of a good repartition of your sequence. So you have the definition here. The star discrepancy is a supremum over all point x in 0, 1 to the s of the error of distribution, the error that you make between the estimation over the interval 0x, so the Cartesian product of the 0xk for all coordinates k, minus the the length of this interval. So you take the supremum over all the interval like this. So this is the definition of the star discrepancy. So we don't have any closed form expression for any discrepancy of this star discrepancy, but we have bounds that are used actually to get the fact that we are in O to the of n to the minus 1. But those bounds, they are just useful asymptotically. So if I take the best known bound for some of the sequences that are probably the best known in terms of error bound, actually, asymptotic error bound, the 0s Niederreiter sequence. If I take the bound in dimension s equal to 5, so I gave the value of the bound for a number n of points, then 1,000, 1.5, 1,000,000, 2.14, 10 to the minus 2, so quite slow, and 10 to the minus 7 for 10 to the 12, but that's a lot of points, and so on. So it's quite okay. But in dimension 25, even with 10 to the 21 points, we still have a bound which is very, very large. And actually, we know that the discrepancy is smaller than 1. So those bounds are very useless also. So we have other bounds that exist, but just to say that in practice, when you use QuasiMonte Carlo, so you just give an estimation and you don't have any idea of the error that you are making. And that's one of the big issues with QuasiMonte Carlo, and probably one of the reasons why also they are not that used. So, but that's a typical numerical analysis issue, I guess. So that's a reason why people like us also worked on a randomized Quasi-Monte Carlo method. So what's the idea of randomized Quasi-Monte Carlo? The idea is that you take your low discrepancy sequence, which is very well distributed over the interval. You just randomize it a bit, but without losing its good repartition property. So by doing that, you keep the convergence rate even for a randomized sequence. And then later on, the idea would be to apply central limit theorem on independent randomization like this. So the most general way to proceed, I describe it for lattice, but actually it works for any sequence, and we also keep the low discrepancy property. But for other sequences, it's just the fact that we don't keep some nice structure, but the low discrepancy property is always kept with this random shift. So the idea is you take your low discrepancy sequence C, and you add to each point of this sequence a uniform over 0, 1 to the S. So you just shift all your points exactly with the same uniform. That's important. And then you take the modulo 1 on each coordinate. So you just all the points that are not in the interval anymore, by just taking the modulo, you just put them again in the interval. And by doing that, you keep the low discrepancy property. So with lattices, you keep even some nicer properties. But as I said, for any sequence, this low discrepancy property will be kept. So that's something that can be proved. So you have other randomization on the digital net by just randomizing digits, but I'm not going to describe them. It would take some time, but the general idea is to do something a bit different. But the general idea is, again, to consider a low discrepancy sequence, to just randomize a bit the sequence without losing the good property, the good repartition property, and keeping the good repartition property in any case. So as I was saying, so the randomized Quasi-Monte Carlo computation. It consists in if you have a budget of n evaluations of h, or to compute the expected value of h of u. So now your idea is to use a low discrepancy of size mn and Rn randomization, independent randomization, such that then you have mn times Rn about n, which is about n, calls to the function h to be equivalent to be compared to an estimator of Monte Carlo with the same number of calls of h. Okay, so Rn is a number of independent randomization, mn is a number of points of the low discrepancy that you are using. So here you have the estimation over a single randomization. So for the jth randomization, you randomize your sequence. You have points u prime I that you index by j, and you take the average value for this single randomization. And now all the x and j are all independent and identically distributed. And what you can do is apply independent randomization and get your RQMC estimator like this as the average over your independent replications. So you can then very simply estimate the variance over a single randomization by using the standard estimator of variance over the Rn randomization. And the general idea is to say, okay, so now I can apply the central limit theorem over Rn randomization and get a confidence interval to obtain this. But you need some theoretical justification to do that. Actually, people are doing that without really justifying it, just saying that if I increase Rn, it should be okay. So what we are going to do here is just to show that to give conditions over which this can be done effectively. So this is based on the triangular arrays and Lindeberg conditions for central limit theorem. So as I said, so the general heuristic to say that I'm choosing Rn, the number of randomization, quite small, and I'm trying to get Mn, the Quasi-Monte Carlo sequence size, as large as possible to exploit the fast convergence rate over Quasi-Monte Carlo in order to get an important variance reduction. Then this is a heuristic which lacks of rigorous justification. So the question is this heuristic theoretically valid? And can we obtain sufficient conditions to obtain a central limit theorem and asymptotically valid confidence interval? So actually, there are some results that exist in the literature. So in a very specific randomization, case of randomization, which is called the nested scrambling of digital nets, and for a very specific low discrepancy sequence, which is actually very costly to apply. So we get a confidence interval even for a single randomization, a confidence interval, and a central limit theorem, and then the confidence interval. So that's something that can be done. But as I said, that's in a case which is very, very specific and which is not very practical because you need to store a lot of things. In the case of randomly shifted lattices or any sequence, actually we have shown about 10 years ago that if we fix the number of randomization and if we increase the number of points of the low discrepancy sequence, then we don't have a central limit theorem. We actually have a convergence to a uniform distribution, so which is something that is a bit different. So now I'm going to describe how to conditions over which central limit theorem can be obtained. So the idea is to, as I said, to have a budget mn times rn, which is approximately n, to have a number of calls to the function, which is n. Okay, and under first assumption 1.a, we want to make sure that Rn tends to infinity. But how fast should it converge to infinity? Because then Mn can also converge to infinity, and it can lead to something that doesn't bring you to something that is Gaussian. So it has to be proved. And in a simple case, in a simple allocation, we can make use of the fact that the assumption that Mn is n to the c and Rn is n to the 1 minus c with a constant c, such that then if c is close to 1, so Rn, the number of randomization, is going to increase very slowly, and the number of points of the low discrepancy sequence is going to increase very fast. So then we can use the fact that use the power of the low discrepancy sequence and the fact that it can reduce the variance quite a lot. But the question is how fast, how big can C be such that we can ensure that we have central limit theorem? How to choose this value of C? So all the results are based on the central limit theorem for triangular arrays, so very standard results. And here we actually have a triangular array since we have Rn variable within each row, which are independent, and all the single randomization, average random, all the average value for single randomization, they are IID with some distribution that depends on n. So that's why the dependence on n complicates the things. So we have a theorem that tells you that if we have this assumption that Rn tends to infinity, then with the Lindeberg, we have the Lindeberg condition, which tells you something about the tail of the distribution of single randomization, standard single randomization divided by the mean, by the variance, excuse me. It has to, if it converges to 0 as n tends to infinity for all t, then we have a central limit theorem. And we have also another condition that we are going to use also, which is a Lyapunov condition, which is a sufficient condition for Lindeberg condition also, which tells you that if we have a moment of 2 plus b prime for some b prime larger than 0 divided by the standard deviation of the estimate of the estimator for a single randomization up to 2 plus b prime, and this normalized. If it converges to 0, then we also have a central limit theorem. So that's conditions that we are going to do. But since we estimate the variance, so we also have a theorem. We also have to be sure that we have also an asymptotically valid confidence interval, and it usually means stronger required conditions by just replacing the variance by the estimation. And we have a theorem that tells you that if we, under the Lyapunov condition, if we have a Lyapunov condition with b prime is equal to 2, so if we have this condition for moment 4 here, total 4, then we have an asymptotically valid confidence interval. So we have been able to show that actually the conditions they depend on the on the variance of over a single randomization. So we have tried to obtain conditions over some assumption on the integrand h. So if assumption 3.a, if we have a bounded variations in the sense of RDN crowds, assumption B, if H is bounded, or assumption C, if we have a moment of order 2 plus B for some B larger than 0. And actually, the conditions here are weaker and weaker. If we have bounded variations in the sense of RDN crowds, then necessarily we have a bounded function. If we have a bounded function, then necessarily we have a bounded moment of order 2 plus B. So for this, so we have been able to obtain conditions that I summarize here in this proposition under the different assumptions over which conditions over which the central limit theorem can be obtained. And we have also conditions over which asymptotically valid confidence interval can be obtained. So now, because I'm going to go faster, so I'm going to look at the case, which is quite interesting, at the case where Mn and Rn are n to the c and n to the 1 minus c. So just playing with how much weight we put on the low discrepancy sequence length, and on how much weight we put on the number of randomization. So here to do that, we make an assumption, which is something that which is not known actually in RQMC, but which can be derived at least for subsequences. So we assume that the standard deviation of sigma for mn points for a single randomization is in theta of m to the number of points to the minus alpha star. So if we are faster than Monte Carlo, then this alpha star is larger than 1/2. And what we want to obtain is what we want to look at is what is the root mean square error of our estimator where we have a central limit theorem, which is, so root mean square is a standard deviation divided by the square root of the number of independent random variables. So if we use the fact that Mn is n to the c and n is n to the 1 minus c, so this is in theta of n to the 1 minus v of alpha star c, where alpha star is just by some simple computation c to the alpha star minus 1/2 plus 1/2. And if alpha star is larger than 1/2, actually, we are always better than Monte Carlo, which is something which is important. So even whatever the value of C. So some conditions for this. So we have a general corollary that's saying that if there exists a value b prime and value k prime such that the moment of order 2 plus b prime of our estimator for a single randomization divided by the standard deviation to the 2 plus b prime is smaller than k1 for all number of mn of points sufficiently large, then which is something that is quite reasonable, but which has never been proved for any in any case. We don't have any counterexample either. But if we have this, then any value of c smaller than 1 will all the central limit theorem. And it gives you, by just applying the largest value of C close to 1, C1, root mean square error, which will be alpha star, which means that in this case, of course, applying randomized Quasi-Monte Carlo is going as fast as applying Quasi-Monte Carlo, and we are able to get a confidence interval. So it's one of the assumptions. Now, again, using our three assumptions, bounded variation of in the sense of RDN cross, H bounded or finite moment of order 2 plus B for a given B. So as I said, this condition is stricter than this one, which is stricter than this one. 3.A implies 3.B, which implies 3.C. So it nicely gives us conditions on the value of CK, which are actually decreasing. So applying a strong assumption on the integrand helps you to put more weight on the length of your Quasi-Monte Carlo sequence. So that's something that that can be proved. So we have many results like this that can be summarized here on this slide. So if we have an assumption on the integrand, which has a bounded variation in the sense of RDN cross. So the upper limit for C is 1 over 2 alpha star. So it depends on the convergence rate of your variance to the -1, and it then gives you a root mean square error, which is 1 in this case. So it's faster than the 1/2 of Monte Carlo, of course. But you have to put some weight on the number of randomizations, and you cannot get, theoretically, at least with our sufficient conditions, you cannot get something better than 1 as a root mean square error, even if alpha star is larger than 1. If H is bounded, so you have a condition which is a smaller value of alpha of C, excuse me, with dependent alpha star, and which gives you a root mean square error of this range, and the smaller also value of C, which is this one in the case where you have a bounded moment of order B. But in any case, you have this the fact that it is larger than 1/2 and better than Monte Carlo. And you have also conditions that we have been able to derive to obtain an asymptotically valid confidence interval. So graphically, if we plot those functions of C in terms of alpha star, so if we see, okay, starting with the convergence rate for the standard deviations, which starts at Monte Carlo and better than Monte Carlo, up to 3.5 here. So the value of C decreases with alpha star. So the better the randomized Quasi-Monte Carlo here for our sufficient conditions, the larger the number of randomization we have to get in terms of the length of the low discrepancy sequence, except for our corollary one, where you have C is equal to C star is equal to 1. And in terms of the convergence rate of the root mean square error, so even if C star is decreasing, the weight that we have to put on the low discrepancy sequence importance is decreasing, the root mean square error, the rate of the root mean square error, it increases. So except for here in this case, if we want to look at the asymptotically valid confidence interval. So we have been able to show here, so that's the conclusion. We have been able to obtain sufficient condition, and I insist on the fact that it is sufficient condition on the randomized Quasi-Monte Carlo methods to ensure a central limit theorem and an asymptotically valid confidence interval. To our knowledge, nobody was looking at that before. And we have obtained result on different situations of on the regularity of the integrand. And we obtained for weaker conditions on the integrand, we obtain stronger conditions on the value of C that have been obtained. So we are currently working on weaker conditions to get something that is closer to what could be sufficient conditions. And actually, we are discussing about that with we have discussed about that with Theorem, trying to see if to have something that is increasing the number of randomization increasing in log n would be sufficient or not. And other situations, other ways to proceed, and that's also discussions with Theorem, is to try, since our goal is to obtain the confidence interval, not necessarily working with the central limit theorem, to work on alternative ways to obtain the confidence interval, such as bootstrap T technique, and that's something that we are currently starting to work on. Okay, so that's it for me. So thank you.
Thank you, Bruno, for your talk. Do you have any questions for the speaker? Just hold
on. Thank you for your talk. So I have a question, is how is the quality of the QMC rule and the order of the QMC that affects the result?
So that's the impact of the quality of the QMC. So it's going to depend on the integrand. So it's measured by the parameter here, alpha star, which is the convergence rate of your standard deviation for a QMC sequence. So the larger the convergence rate, with our sufficient conditions, let me just the larger, so alpha star measures the efficiency of the Quasi-Monte Carlo method, and the larger the efficiency of the Quasi-Monte Carlo method, usually except for AVCI in a single case, but the larger, the better the efficiency of your estimator, which even getting a confidence interval, so which is the root mean square error of here is the rate of the root mean square error. So that's measured by the alpha star. So I don't have curve, but if you on those slides, but that's typically if you apply randomized Quasi-Monte Carlo methods on some simple expression of integrands, but you obtain convergence rates which can be n for the variance, which can be n to the -2, usually n to the -2, or n, even in some cases n to the -3, 4 for simple integrands. So much faster than n to the -1 for Monte Carlo.
Thank you.
Hello, Bruno. This is Raul. How are you? Thanks for the nice talk. Bruno, regarding extensions to infinite dimensions, have you thought of this work by Kuo and collaborators, where they they extend the Quasi-Monte Carlo to infinite dimensions, essentially by assuming some summability properties of the integrand. So would you think that in that case one can extend the results that you have on this central limit theorem? Because there's a double limit here on the number of points that you take for the quadrature of Quasi-Monte Carlo versus the number of randomization, right? This is what plays a role. But if you start letting the dimension of the hypercube get larger and larger, but you have some ability in the mixed regularity of the derivatives, can you still hope to get a central limit for that case, for those cases?
Yeah, for the general result that we have, I don't think it's a problem. I think it can be used in this case. The point is that if you increase the dimension, usually Quasi-Monte Carlo performs more slowly. So it probably means that this value alpha star is going to be closer to Monte Carlo, except if you have some properties on the effective dimension, which is slow.
Yeah, that is what they assume. Essentially, they assume that there's some kind of summability in the derivatives that they use for this Klaka inequality. So they keep the rate. So if they keep the rate, I would assume that maybe there's a way to get a corresponding central limit theorem for that case.
For me, there's no problem in this case.
Great. Okay.
There's no problem. But you know, that's a work in progress, and I'm not very happy with the fact that we only have sufficient conditions. So that they are probably not that tight. Okay, so that's why we are currently working on having weaker conditions, better to put more weight on the length of the low discrepancy sequence rather than on the number of randomizations. So that's something that we can do, and numerically it probably works also.
Hello, many thanks for your nice talk. So just to follow up to Raul's question, so in Ewan Sloan papers and colleagues, they showed that if they consider kind of weighted Sobolev spaces, assuming some sufficient mixed first derivatives, then they get a rate of 1/n for any dimension. So the question first is that if you use such kind of bounds, does it help to relax maybe the assumptions that you have? I mean, because your assumptions depends on the bound that you are using, which is the variational bound in some sense. And the second point, how can you comment on the link between them?
Yeah, so I don't remember exactly how they proceeded, but in terms of it depends. That's probably another condition that can be used, something that could be added in this case. I'm not 100% sure, but that's probably something that can be used to get another type of results. So I don't remember exactly how they proceeded. So it's hard to say how it can be obtained. The corollaries can be obtained, but that's probably something that can be. We could add assumption 3.d or something like this, and obtain a new sufficient conditions in this case. But we have to be sure that I don't remember because it depends on the low discrepancy that they are using and what kind of randomization that can be used in their case. I don't remember.
Do we have any further questions? We've got plenty of time. No, I have a couple of questions. Thank you for the nice talk. In the context where you do Markov chain quasi-Monte Carlo, is there a kind of standard practice to compute confidence intervals yet, or is that not, the technology hasn't got that far yet?
It's the same story. So in that case, you have to use independent randomization over all your whole path of your Markov chain, probably. And so that's something that we did with Pierre Lécuyer, array RQMC this is RQMC for Markov chains. And Pierre and I are do not always agree about the application of a randomized Quasi-Monte Carlo. So for me, it's important to have a sufficient number of randomization to obtain an idea of the error thanks to the central limit theorem. And Pierre is saying that, well, just use the 5 randomization and you get an idea of the error. So that's not, so it's very practical in this sense. So I want to have some guarantee and some to be sure of what I'm doing. And Pierre is not that worried about that. But in the case of Markov chain, you would have to apply RQMC several independent times over the whole path of your Markov chain and to apply it independently and get a confidence interval again. And you get the same questions about what's the number of randomization which is sufficient, especially if we increase the length of the number of chains to parallel number of chains by QuasiMonte Carlo to ensure a valid confidence interval and a valid central limit theorem. But you have to apply it independently.
Thank you. Do we have any further questions? One more.
Go ahead.
Yeah, thanks for the great talk. You've talked at length about the difference in convergence rate for Monte Carlo and Quasi-Monte Carlo. I was wondering if you could also say something about the constant, maybe, because for the central limit theorem for the Monte Carlo, we know that the constant is the variance. I was wondering if it's similar in the randomized Quasi-Monte Carlo setting.
What do you mean the constant? You mean the constant before the n to the minus something, or?
Yeah, we say that it's O to the n to the minus alpha star, I guess.
Yeah.
Yeah, I was wondering what the constant factor would be, especially for small n.
So that's it's hard to say something. So there's no proof of the exact constant for randomized Quasi-Monte Carlo. So the results that exist are the constant for the discrepancy. So let me come back to this. What exists is the results that have been studied a lot is the expression of this discrepancies for the different low discrepancy sequences. So you have, it is upper bounded by it is in a constant times n minus 1 log of n to the s, and the constant depends on the low discrepancy sequence. So to have, and for this, using Niederreiter sequence is the sequence that minimizes the constant before the n to the minus 1. And people in Quasi-Monte Carlo area, it was 20 years ago, and now there's not so many things going on the generation of sequences like this. So then people started to work on the constant in the constant, limiting it, and then in one constant in the constant of the constant. So it became, and the sequences became more and more complicated, and to gain almost nothing. But the only results that exist are for the expression of the bound of the discrepancy and which sequences are minimizing the constant before the n to the -1. For our QMC, we don't have any result. We typically, I have not experienced a constant that is really larger than what you have for Monte Carlo in practice. But it doesn't mean that it cannot exist. But usually we have things that are of the same order. But there's no proof about that. The only proof about the constant is for the different low discrepancy sequence and when computing the discrepancy of those sequences.
Okay, thanks. Yeah, because in Monte Carlo it's quite simple. You estimate the variance basically.
I agree. I agree. And then you try to minimize the constant. But here in our case, we try to minimize the convergence rate.
Yeah.
Because you can with Monte Carlo you cannot play with that. So I understand your question and I agree with your question.
Okay. Yeah, thanks.
So I guess no more questions. If not, let's thank the speaker. Thank you very much, Bruno. So that concludes this afternoon's session. We resume at 4 o'clock with the talk of Dan Crisson and Alexander Loeb on deep neural networks for the nonlinear filtering problem. Thank you.